Okay, now we can sketch the asymptotes by using the frequency that we get from the previous calculation. Okay, so take a look at this formula. Okay, this is this formula, we can say that it is approximate analysis equation. Okay, for this one we get the asymptote. Okay, remember what is asymptote? Asymptote is a straight line that has a slope equal to 20 dB per decade. Okay, so we have to find 2 points, okay, to draw a straight line, okay, which is we get from this. Okay, so in this equation we see there is a F1. F1 is actually the FLE, FLC and FLS, and another F. This F is actually this value. Okay, you can see for this value. Okay, can you see why the frequency value for the FLE here is different from the FLC and FLS? Here is 10, 100, 1, 10, 0.1 and 1. Okay, I will explain a little bit here. Okay, the FLE now is 327, okay, and FLC is 25.68 Hertz, FLS is 6.86 Hertz. Okay, to draw the asymptotes for the low frequency response, it should be like this. It facing to another side here, so we call this, it has slope here, which is negative 20 dB per decade. Okay, the slope is here, like this, and so during this time, okay, at this point, okay, to draw the asymptote, this point is the actual frequency that we get if this is the FLE. Okay, this point is equal to 327 Hertz. Okay, so to get another point here and here, so we take a decade in front of this 327 Hertz, which is somewhere here. Okay, so 327 is in the range is from 100 to 1000 Hertz. Okay, for 327, right? So we take another decade here in front here. So let's say this is from 100 to 1000. So we take another decade in front of the 100 is from 10 to 100. Okay, so we get another one is 10 to 100. Then for the 10 here, like it can become another one is 10 to 0 to 0.1 to 10. That's why this point, you see, is at 10 and 100 here, 10 and 100. Okay, because of this. Okay, let's say for another example. Okay, we go to another example. For the FLC is 25.6 Hertz. Okay, so 25.6 25.68 Hertz is at range 10 to 100 Hertz. Okay, so this is 25.68 Hertz, the actual value for FLC. Okay, then to get another point here, it is actually, we take 10 decade, so 25.68 is at 10 to 100 Hertz. Okay, so here is 10 and this is 0. This is 1 to 10. Okay, 1 to 10, the range. Okay, so we take another point in front of it, so we get 1 and 10. Okay, and take a look for another example for the FLS. The FLS is 6.86 Hertz. 6.86 Hertz. So it is in this range from 1 to 10 Hertz. So this is the actual value. So 6.86 Hertz from here. And then another point here. Okay, 6.86 is at 1 to 10 Hertz. So we take another decade in front of its value, so it becomes 0.1 to 1. You see, 0.1 to 1. Okay, this is because its range for the frequency is different. That's why I take a different range for the for these 2 points. Okay, now once you set this value, then you just calculate directly using this equation. So by using this formula, and this formula, you get this value. Okay, after that, plot these 2 points on the graph. Okay, see, this is we draw the gain in dB versus the frequency, okay, in log scale. So remember here, okay, this is in log scale. Okay, and here AV is in dB, okay, in decibel. So for the first one, okay, when we draw each point here, so we calculate, okay, let's say this is for the frequency 6.86. 6.86 is FLS. Okay, this is FLS. 25.68 is FLC. FLC, and this is FLE. Okay, so the actual number or actual value 6.86 is here, mean at this line. Okay, and 25.68 at this line, and 327 Hertz is this line. You see, this value is in this range, 100 and 1000. But to get its point here, so we took a decade in front of its value. So for the 327, so this point that you have calculated previously, okay, so you get from this one and this one, this one and this one and this one, then you plot in this graph. So you get this point, this point, this point, this point, this point, and this point. Okay, you will get from this. So you refer the gain value take a look at this side, okay, and its value, okay, here. So once you get 2 point here, and you can draw a straight line, okay, you can draw the straight line. Okay, remember that during when you do this, actually you will not see this value first. You will get these 2 point first. Can means that you plot this value, for example, for the 6.8 hertz here, I get 0.1 at the 0.1 hertz here, 0.1 hertz, I get negative 36.7. Negative 36.7. So the point is here. Okay. Then for the point number 2, when frequency is 1, the gain is negative 16.7. So 16.7 is here. Negative 16.7. So this is a point number 2. Then when I get these 2 points, so I can draw a straight line from these 2. Then it will cut to this area. So this point, so this point is actually the number that you calculate from here. Okay, 6.86. Okay, and it will continue for another frequency for the FLC, FLE. So now you get 3 asymptote. You can see this asymptote has same slope. Okay, slope is 20 dB per decade, because you have you see from decade to decade, from 10 to 100, and you get this this height is 20 dB and its width is decade, 10 decade. Okay, it's 1 decade equal to 10. Okay, now we go to draw the low frequency response, or we say that this is the actual response or curve. You already get the asymptote. Okay, so to get this one, you have to use this formula. Okay, this formula, actually the first formula, you insert your frequency here, 127. Okay, for this one, you only choose one frequency. Okay, which one is the cut-off frequency? The highest one. Okay, the highest from FLC, FLS, and FLE. So that one will become the cut-off frequency, and we only calculate once. Okay, so 327. So once you calculate, okay, this frequency, okay, we take many points compared to the asymptote because we want to make a curve. The curve is like this. So assume that you will take many points from the beginning. Okay, so I start with the 0.1, 1, 10, 100, and 1000. Why 1000? Because my frequency is at this range. Is here between 100 and between 1000. So I need more points, okay, to get curve at this side, right? So my frequency is somewhere here. Okay, so when you calculate here, so you replace this frequency with 0.1, with 1, 10, 100, and 1000. Then you get its value here. Okay, Then we plot this value. Okay, this value is from this number, this okay, and then we plot here. So when I plot, okay, for the frequency equal to 1, frequency equal to 0.1, 0.1 is not enough for this curve. So 10, 100 and 1000. Okay, during frequency equal to 1, and this is the value around 50, and during frequency is 10, you get here around negative 30 dB, and for 100 we get this one, so the gain is negative, around negative 10, and 1000 is somewhere here. Then once you get this point, and you draw this line. Just draw this side, and at this side it's something like this. Okay, after that, don't forget to label the negative 3 dB point. Okay, at this side, at this point, okay, I measure here negative 3 somewhere here. So I get this point. Here is negative 3 dB. Why is so important about the 3 dB? This is because the cut off of the low cut off frequency happen at here. It means that your cut off frequency is at this point. Okay. So during this time, the gain is not 0 but negative 3 dB. There is some losses here. Okay, so when I combine all this graph, all this curve and asymptote, when we combine all this asymptote, we get something like this. Okay, this previously we make these lines and then the curve. If you see that asymptote for this one, okay, is the nearest. Okay, it shows that the actual response happened because of this frequency. And you remember that the negative 3 dB is somewhere here, negative 3 dB, don't forget about this. So during this time, you get this curve. Okay, so that's all for the low frequency response. If you can sketch the asymptote and the curve nicely, and it's done.